think we'll wait a couple more minutes as people start showing up, and then we'll do introductions and get started. All right, Jeremy, think you're ready?
I think so.
All right, let's do this. So welcome everybody to one of the first events of the 2021 LD4 conference. This is the workshop for visualizing and training Sinopia Linked Data with Pandas, spaCy, and PyTorch with Jeremy Nelson. If you're in the wrong place, feel free to stay. It should still be interesting. So Jeremy is a software engineer at Stanford University Libraries. His areas of focus are on development of linked data systems, like Sinopia and other things, and applications of machine learning within the library. Before we get started, a few administrative notes. The workshop will be 3 hours and 15 minutes, thereabouts. The first hour will be with 55 minutes with a 5-minute break, setup, analysis, visualization of Sinopia linked data. The second hour will be 55 minutes with 10-minute break. It'll be NLP using spaCy and HuggingFace transformers. The last hour will be 55 minutes, training and testing with FastAI and PyTorch. And then the last 15 minutes will be general questions and answer session. As far as questions go, Jim Hahn will be watching the questions through multiple sources, but the best way to ask here is to ask through chat in Zoom. And also you can just, Jeremy said he's fine with people just sort of unmuting themselves and hopping in with questions. So feel free to do that. And with that, Jeremy, you can take over.
All right. Well, thank you, Joe. And thank you, Jim, for moderating and leading the session. A couple of things. I will be sharing my screen, but I want to emphasize that this is more of a workshop. So I'm hoping that all of you will be able to actually sort of follow along in some of the environments I'm going to show you. So I'm going to go ahead and share my screen. And what the first thing I want to do is we're going to go through some Jupyter notebooks, and then so the entire session is structured in, and there will be 6 Jupyter notebooks. 1, 2, 3, 4, and 5 will be the actual content. And then the last one is sort of answers through some exercise I've sort of sprinkled throughout the notebook. So this will give you a chance to actually apply some of the things that we're going over. And then if you need to, you can check those answers with that last notebook. So to get really started here, we're gonna start with like the introduction and setup for Sinopia's knowledge graph, which we'll explain a little bit more, but basically the knowledge graph is a RDF graph that has some additional functionality on it that I think is helpful to use, but that's sort of where we'll start. So this workshop is really just an introduction to some of these technologies and techniques. I want to emphasize that don't expect to be a machine learning expert after the session, but I would say this should give you some at least starting point on a number of these different techniques, and you'll be able to sort of explore those. As Joe already mentioned, we're going to be breaking this workshop down into 3 sections. We'll start off with introduction, setup, analysis, and visualization of Sinopia RDF. Then we'll go to actually using spaCy and HuggingFace, which are 2 different technologies for doing machine learning. And then in our final session, we'll be actually training some models and using fast AI and PyTorch. So as I mentioned before, I'm hoping that this will be more an interactive session or workshop. So there are a couple of ways to run these notebooks. I think the easiest, and hopefully everybody will be able to do this, and I'll also pop this into the Zoom chat as well. Probably the easiest way is just to launch this using a service called Mybinder. So I will put this into the chat. And if you click on that, and I will sort of do the same here so you guys can see, this should bring up this Mybinder, which will start loading, and then it'll actually launch you into the session itself. And you can kind of see it's going through basically building in the back end a Docker environment of this workshop. And then you'll be able to actually open up these notebooks in your own machine if you want. At the end, you should see something that looks similar to this screenshot here, where on the left will be a listing of the workshop or the notebooks. There's a couple of Python helper libraries or modules that I created for the session, and then you'll be able to actually click on the first one, the introduction one, and that should launch it. And you should see this basically the same notebook that I'm showing you right now. If you want to, and it's a little bit more involved, but you can also run this locally. So basically, you'll just need to, if you don't have it already, download the latest version of Python. Once it's installed, suggest creating a Python virtual environment. You'll need to activate it, then name of repo. Let me update that. And also pop this into the chat as well. So this is actually the GitHub repository for this presentation and this workshop. So you'll need to clone that, and then after you've done that, you'll need to restore the requirements. Then you can launch the Jupyter workshop, and then it should be running on your local and desktop or laptop at localhost :8888. So at that port number. However, Jupyter Lab is smart enough that if you have another service running on that same port, it'll go to the next one. So it'll go 8889 where it'll be launched. First thing, after you have this the Jupyter on Mybinder launched, you'll need to run this cell right here to actually extract the data. And I'm going to, as it's sort of loading, and probably for everybody else, as you're waiting to launch it on Mybinder, I'll give you a quick little overview or introduction to Jupyter Notebooks. So Jupyter Notebooks and Jupyter Lab, which is sort of a extension of Jupyter Notebooks, is really a popular computing environment in the big data and machine learning. And it all runs within your web browser. And so a notebook, kind of see right here, is made up of these cells. So each one of these things that I'm clicking on are different cells, and the cells can have different types. You can either add in Python code to do computation, or you can switch the type and you can actually create markdown. So you can combine in your notebook both textual or documentation, as well as adding in Python code to run things. And here you can kind of see, here's the, each of the notebooks has a toolbar, and there are some important buttons on those toolbar. One, if you want to save your notebook, so as you're creating a notebook, it's good to be able to know when to save it. And so we're just clicking on the disk will do that. If I wanted to add a new cell to a notebook, the plus sign. So right here, this will add a new sort of blank cell. Now the cell, sort of the default type of a cell is as a code. So if you need to change it, then you'll want to actually click on this markdown drop down to change what type of cell it is. You can also delete the current cell that you're in with the scissors icon. You can copy the current cell. You can paste it in your current cursor location. And then really, I think a very important one is actually running your code or rendering the markdown. So, and that's this play button, if you will, just as a sort of convenience function. All of these commands also have keyboard equivalents. We won't go through all those, but as you're working, just hitting shift return or shift enter in a cell will run it. So you don't have to go back up and run it. So, and then there's an example of sort of that drop down where you can specify this. So that's really a very quick introduction to Jupyter Notebooks. Just to give you a little bit of context also, this year when I attended virtually the PyCon, the large Python or largest Python conference, one of the keynote speakers who works in the medical field was talking about how especially with the medical startup community, and as they're working with hospitals, doctors, pharmaceutical companies, before, when it was really difficult between all these different systems that have very sort of specific systems that have different data formats and everything, it was really difficult to sort of pass on and to use other people's data in your research or work. And he said that sort of in the past probably year or so, particularly with the pandemic, really the big change is that all these researchers are now doing all their work in Jupyter Notebooks, and they're sharing these Jupyter Notebooks across these different organizations. And that's what really provides them this environment to be able to sort of share data as well as create custom views into their data using the Jupyter Notebook environment and user interface. So I thought that was sort of interesting, and I think it's a good way for us to sort of share work that you may be doing in these environments. Let me go back and see. Okay, so you'll notice here that this is set up. Now, this is a weird quirk that I discovered last night. When you see this view, you're going to want to go up to the URL bar, and at the end it says tree. You're going to want to switch that to lab. And when you do that, it actually brings up the Jupyter lab environment. You'll need to do that because if you have it just in the previous viewpoint, none of the computations for whatever reason are going to work. So you want to switch this to the lab environment. And so this is what you should see then. And then if I click the first one, and so there you can see the first notebook that I'm showing you here. Now, you notice I am running this locally on my own environment, so that's just, but it should be the same Jupyter notebooks in either one. All right, now let's actually start using this notebook to get at or generate data from Sinopia. So Sinopia, we have a Sinopia API, which, and in each environment has our own API sort of endpoint. So right now in Sinopia, we have 3 different environments: development, staging, and production. And each one of those environments has its own API endpoint. So that's something to be mindful when we're doing this work. The API also provides you different ways to sort of query. So you can, for example, query by groups that are in Sinopia. You can also query by type or class or RDF class for particular resources. So here's sort of the general pattern for the API, where it's HTTPS API period. Now both development and stage have their environments as part of the URL. The production does not. So for production, it's just api.sinopia.io, and then / resources will give you every resource that's available through the API, or if you can pass in the group name. So What I did to sort of help you, instead of everybody needing to memorize this, is that there is this, so first thing, make sure that you run this first cell. So that's going to load up all the dependencies that are running. And now, if I go back here, we can see we have this little widget now. And so you can select which environment, you can select a particular group that are all available, and then you can just copy that URL. Before we go on, and I'll demonstrate this in the, so notice, again, I'm running that first cell there. And then we'll need to actually unzip all the data that we have. So at this cell, I'm going to go ahead and run this. And the sort of convention or how these cells work, if you put a exclamation point, that will basically run this command in a virtual shell. So these are actually, if I was running from the terminal, this would run this command. And you can see here, this inflated our data. And now if I go into this directory, you can see there's all the data we just extracted. So you'll need to make sure that you do that as well as you're running this. Now, going back to my local notebook, the next thing to kind of show you is that I also created in this helpers Python module some functions just to help us as we're working on various tasks within this workshop today. And so here I'm calling in the helpers module this create_kg or create knowledge graph. And here you can just pass in any of the URIs that you're sort of dynamically generating. So you can copy these, and then that will go out, that will query the API, extract all the RDF from those resources, and combine them all into a single RDF graph that then gets wrapped in this knowledge graph. And then it returns that. So then we can use this, this function call, and we assign a variable, and now we can access that new knowledge graph in subsequent cells within our notebook. So I'll just run the PCC real quick so you can kind of see what this sort of looks like. So there's a little sort of status bar that will tell you about, I think it's every 25 resources as it's going through. Some of the work that we'll be doing, so that finished, so we have approximately, well, we can actually see how many triples that were extracted. So I'm just going to do that real quick. And in the knowledge graph, you can access directly the graph by using the RDF_graph method call. And now what I'm doing is I'm just going to get this len as a Python keyword to get the length of a particular data structure. In this case, we're just going to get the length of all the triples that are in this graph. And so for the PCC and stage, we have 7,364 triples as of a couple of minutes or so ago. So this API and this function actually does in sort of real time, goes out to whatever environment or API endpoint you're hitting, and will extract everything that's currently available at that point. As a lot of the work that we're going to be doing is actually, we'll be demonstrating on the full data set that's available, all the RDF resources that are available in each environment. So here, we sort of have a function. I'm not going to necessarily, or I want to advise you to run this because it takes about 8-9 minutes. But fortunately, yesterday or the day before, you can save these graphs, and all the stage environment is in our data in this stage.json file. So instead of running all these, and I'll just run that sort of in the background so you can see as it's as it's sort of constructing it. And then I also sort of wrap this, if you notice in the cell, just to provide us a start time and an end time, just to see how long it takes. But for on your own, in your own notebook that's running on Mybinder, I'll go here, and instead of running that in real time, you can kind of see there's our environment, our sort of widget there. I'm just going to run this cell that will load that. And so it takes probably a minute or so to load everything. And if we look here, it's in this data directory on the left here. We're just loading this stage.json file. That's that serialization. So that's running. And so you'll, if you're running this on your own in Mybinder, I would advise just using this. But if you want to spend the time, you can run the full environment or harvester. So it's sort of up to you if you want to do that. But this way, this will be a little bit faster, and we're not waiting for the full 7 minutes or what have you. So I'm going to go back here. You can see it's still chunking along, or cranking along there. Then I also put here as sort of an example. Once you sort of save that, you can also, the knowledge graph has this really some convenient functions to easily save or persist your data. And it's just this .save_JSON LD. So saving the graph and everything as JSON linked data. And here in the next cell, we sort of start, and then I'm just extracting the production. And again, just so if you don't want to do that, there's also the production.json is also available for you. At the end here, I have this exercise, and if you have the Jupyter notebook loaded, here's something that I want you sort of to try to do, given how we've structured everything, is that the National Library of Medicine is one of the institutions that use Sinopia. And so sort of as an exercise for you to do, and we'll probably maybe spend, I'll let you work on it 4 or 5 minutes. Try to go and see how you extracting all the triples for each environment for the National Library of Medicine, and sort of you can then compare how many triples are in each environment. So I'll come back in like 4 minutes or so and just sort of see how everybody's done. If you're running into problems, let me know now or post it in a chat or anything. And because of our time constraints and how many people are on this call, I'm not sure I can help everyone, but if you have you're totally not working, either post in the chat or let me know, and we can, maybe it might be an easy fix. So, all right, so I'm gonna pause here, and then while it's going, we can sort of watch to see the actual real-time harvesting of Sinopia's stage environment.
Hey, Jeremy, there's a question about output in the, oh, you got it, okay.
Yeah, so I noticed, I think it may be because you're running just in the notebook mode and not in the Jupyter Lab mode. So I would go and switch out and remove the tree and put in lab, and that should bring up the lab environment. Then you should see the results. So that was sort of the problem I was running into yesterday. And so I think you may make sure that you're in lab mode and not just the notebook tree mode. All right. Hopefully that solved your problem, Lynette. Let's see. Yeah, you'll need to remove the tree and add lab at the end of the URL. So when you bring it up, it should look like something like this. You notice clear at the end. It should be lab, and then once you bring up the lab environment and you click on one of the notebooks, then it'll be lab/tree and then the name of the notebook. If you just have tree /lab, then the output it won't work. And I'm not sure why that's happening, but I didn't have time to sort of troubleshoot that problem. But make sure you're in the lab mode to run this on Mybinder. All right. I'm going to go ahead and show a couple of things while this is running. Notice when I'd actually loaded up the number of triples, we can see in our stage environment, we have over 500,000 triples now that have been cataloged over the past couple of years in Sinopia. If I go back here, you'll notice that there's the Sinopia stage data is not necessarily clean, and there are some invalid URIs and things like that. And then there's some resources that are entirely missing the RDF. So part of what this helper function does, this harvest method, is it will ignore those resources that don't have any RDF data, and then it'll try its best to sort of manipulate the URL to make it a valid URL, because we're going to want to have everything in place in the RDF graph for our subsequent work that we'll see next. And right now you can see sort of in real time, we're close to 9,500 resources, and maybe we'll pop back and look at that just to see where we're at. But we're close to harvesting the full RDF from stage right now. So the next thing I have us do is we're going to start looking at the next notebook. Again, first thing I want to do is make sure I'm loading up the first cell. So that will again loads up all the dependencies and other sort of third-party modules that we're going to be using, and also it loads up some of the standard modules from the Python standard library. So I'm going to switch a little bit focus, and I'm going to show you how to actually create just a small graph of a set of BibFrame resources that have been cataloged in Sinopia. And so you can kind of see a much smaller graph, and we'll visualize that graph as well. So first thing is there's a listing here of BibFrame resources. So there, if I clicked on that, you can actually open up and you can see what the sort of default serialization that's provided by the API. In this case, everything's in JSON or JSON linked data. So here we have our work, we have the work admin metadata, we have the instance admin metadata, and then we also have the BibFrame item here. Now in this next cell, and I will run the cell here. This just, I just have all those links now in a single list. And then we're going to actually create our graph. So here I pulled in a couple of namespaces. And then from the RDF library, we're going to create a graph, and then we're going to bind the BibFrame and the Sinopia namespaces to the graph. So I'll just run that. Now we're going to iterate through all those resources that we've defined here in the Sinopia _stage _ URLs. And then we'll just add those to the graph here. And so I'll run this here. And so sort of the process, and the harvest method that's in the helpers module does this as well, is that we're going to go through each of the URLs. We're going to extract it with the request module. So that's a web or HTTP library that's really convenient to use. And we'll go through each of those URLs. We'll save the results. And so what comes back will be all this, everything that's here in a particular record. Then we'll extract the JSON. Then in the RDF graph that we just created, we're going to parse it and I'm extracting just the data. So in Sinopia, in all of our resources, all the actual JSON linked data, the RDF, is in the data property. We also have in the resources additional metadata, and you can kind of see this if I go down here to the bottom. Here is the data property, and if I scroll down to the bottom, you can see we also are storing other metadata associated with the Sinopia resource. So we have the user, the group, which template ID we use, and then some helper sort of properties for like the metadata. If there's any items that are referenced or instances, in this case, since this is a work, this references the BibFrame instance. We have any work refs, the ID, which is the same as the last part of the URL. We have the URI, so the complete URI, and we also have a timestamp when it was created. So I'm going to run this real quick. So you can see I just outputted so it was pretty quick to run through those 5 or 6 resources. So we started off with 0 and we ended up with 136 triples. And one thing that's I like to do when I'm working with RDF is just sort of as a sanity check, just to see what that graph looks like. So I'm going to go ahead and I'm going to grab the graph here. So let's see here, this PCC graph. I'm going to serialize it, and because I think Turtle is a little bit easier to see as a human comprehensible serialization. So here I'm just printing out this serialization, and you can see here's our work, there's the admin metadata, all this data that's associated with it. Also, it has the labels for a lot of the external resources that we're using here. Here's the actual work metadata, admin metadata. Here's our instance, and here's the instance admin metadata that was listed there. And let's see, did I skip over? We should see the item here somewhere. There it is. So we don't have that much information in the item, which is ideally, the whole BibFrame model is our most general information is contained in the work. As we get more localized, we put triples or associate triples in the instance, and then finally the most specific triples are in the item. So, and then they're all tied together with triples. And so you can see here that the organization who's it's held by, sort of the shelf mark or call number, and then in Sinopia we have what resource template was used to create a particular resource. So going back here, okay. So I just wanted to show you real quick. Here is our full Sinopia stage environment, and you see it took us 12 minutes to in real time to extract all the resources that are in stage. So the sort of step 4 now that we have this graph available, is we're going to pass it in this KG Labs and actually create the knowledge graph. And again, the knowledge graph really wraps and provides additional functionality on top of the RDF graph. So we'll just right here sort of name our knowledge graph. And then here, this import graph parameter is we're passing in that RDF graph we just created. And so I'll go ahead and run that. Now, the knowledge graph provides some really basic information, sort of as a graph level on what's happening. And it allows us to sort of analyze the shape and structure of the RDF in our particular graph. In sort of graph now, we'll have a really brief introduction to some standard graph terminology. A node is really a fundamental unit. And in our RDF, in this case, so an RDF is known as a directed graph. So what that means is that there's definitely a structure to how the relationships are created within your graph. In RDF, a node is either a URI or a blank node. And typically those are either in the subject role. So in RDF, the really basic fundamental level is a triple, and a triple is made of a subject, a predicate that is sort of defines a relationship, and then the object. So in our RDF, in terms of a graph terminology, a node is either a subject or an object. And in the object node, it also can be a literal. So we can actually store data in RDF in the object. An edge in graph terminology is that linkage. So in this case, our edges are defined by the predicates, which really connect the subject and the object. And then the KG Lab, our knowledge graph, provides some metrics that we can run against our graph to kind of get a sense of what's happening. So I'm going to go ahead, and the first thing we do is we're creating a measurement object where we're going to pass in our knowledge graph, and then we're just going to display how many edges a particular graph has and how many nodes it has. So I'm going to run that real quick.
Hey, Jeremy.
Yes.
Sorry to interrupt.
No, you're fine, please.
There was a question about the what the text was that you put in for the command with turtle.
Oh, sure. I can go back and show that, and I can also put that. So here I have the graph. There's a method called serialization. So that's gonna you can specify different serializations. So you can do turtle or in3 or XML or JSON linked data, and I'll just put that in the chat as well so people can see that. So that's all we're doing. We're just sort of serializing it and then printing it out to the output there. Now let me scroll back down. Another convenience of a Jupyter notebook is if I want to sort of suppress the view, I can click on the left, and what that'll do is it'll close that particular output of a cell. So if you want to go back, we can open it or close it, and it just makes it a little bit easier to navigate your Jupyter notebook in this case. So we can actually, now that we have this measurement, we have this idea that in our particular graph, we have 136 edges and 72 nodes. We can just test to make sure that the number of predicates equals the number of edges. And so what I'm doing here, the graph has the RDF graph and the underlying library that we have, RDF lib that we're using here in the notebook, has this convenience function just called predicates. And that just returns back a list of all the predicates that may be in your particular graph. So first thing I'm doing is running that, just collecting that list, and then I'll print out and sort of compare the number of predicates and then test to make sure that our length of our predicates, which we see here, is equal to our edge count. So I'm going to go ahead and run that. And then, yeah, so that is confirmed that we have 136 edges and we have 136 predicates, and then our test for equality, it came back true. So that just, so again, a little bit of a way to double check to make sure that we kind of understand what's happening with a particular graph. So the next exercise, and maybe we'll do 4 or 5 minutes here, is I'll have you go out and look for a BibFrame work, and hopefully you'll be able to find a BibFrame instance and try to replicate this this code here. We won't spend a lot of time on it. If you want to go back and do this exercise, you can, but I want to just give you a little bit of an opportunity to do this on your own, sort of creating the small BibFrame graph, and sort of give you an idea. If you go to, for example, stage environment, I'll show you an easy way to do this. You go to search, and if I search for everything, I can actually filter by class. And if I just want to say, show me only the works and go, this will give you a listing of all the works. And then if you select one of these, for example, and that have the API URL, go down here and you can see if there's a BibFrame instance that's associated with a particular work. And it may not, so it may take a little bit of work on your part to find a particular BibFrame work and instance to create this graph. So we'll say another 4 minutes to do that exercise, and then we'll go on to the next part of the workshop. All right. I realize that's not a lot of time to go out and search for a BibFrame work or a corresponding instance, but just because of how much we have to get through, I don't want to spend too much time. But again, if you get really stuck in the 06 notebook, I basically created answers or examples for all the exercises there. So if you want to go back to sort of refer to that, you can see what we're doing. So one of the really, I think to me, cool things about the KG Lab Knowledge Graph is that it has some neat visualizations, sort of graph visualizations. So the first thing we're going to do is, so we're in this visualization, we're going to create a subgraph, basically create a tensor, which is, if you want to think about it, is sort of like an array or a collection that's been converted into a numerical value. Tensors are really fundamental to machine learning, and but we won't spend a lot of time here, but sort of this visualization converts our graph into a tensor, and then it calls this PyVis library. And if I run it here, we have now all of our triples are now sort of, let me kind of go into this. You can kind of see, if I want to move, you can kind of see all the different types of nodes and the connections. So here, the example is our, let me go out a little bit. So you can see how the nodes are different connected, how all the triples are constructed, and you can sort of move this around. And now you could run this against all, the 500,000 triples that we have in stage, but then you have a super dense graph that's really hard to actually use. So this is just, I think, a better visualization for smaller size graphs. And you can see, even though, in this particular graph, we only had 72 nodes and 36 edges, you can see it is sort of complicated, but very interesting to we talk about linked data a lot. We talk about BibFrame as a linked data, but really it's all this sort of graph. And this is our bibliographic graph, if you will, of this particular BibFrame graph that we created. And you can do the same on any sort of resources in Sinopia that you want to use. Maybe if you do a search on a particular group, you can do that as well. But I found this sort of really interesting visualization of what a bibliographic graph looks like in Sinopia. So let me scroll down here. So now we're going to switch gears a little bit, and we're going to go ahead and load up, because we had saved all the stage triples. If you run this cell, and we'll take a couple of minutes, but it'll load everything up and then display, and there's our number of triples that we have. So this is I've just loaded in into this stage underscore KG graph all of our triples from stage that was harvested over this weekend. So first thing, let's just take a look to see what the sort of measurements will be. So here I just create another measurement object and pass in our stage, and you can see here we have all of our edges and all of our nodes. Now, so what's really cool, I think, and what I'm pretty excited about these knowledge graphs, is that you can create a Sparkle query against your graph, and you can return it as a Pandas Data Frame. And I'm not going to spend a lot of time on what a Pandas Data Frame is, but I would say, think of a Panda data frame as a two-dimensional data structure that's very similar to how we use spreadsheets. So in a graph, or in a Pandas data frame, you'll have columns, you'll have rows, and then we can do a lot of things with the data that's in that. So here in this cell is, I'm just going to query our graph and return back all of our classes that have been identified. And so I'm going to run that. Again, this is sometimes especially if you have, because it's going to return back a large subset of data, it may take a couple of seconds to run. Now we can actually, because it returns back and we've saved in this variable, this class is underscore df, I can get a sense of how large it is. So here we just have one class. So we just have basically one column called class, and we have 112,079 rows in that. And if we want to, if I just type in head, we can get the first 5 rows and display it. So this is what we have in our graph. Now, what this next line is it's going to actually go through and count the occurrences of all the different classes. And here, so I'm going to take off this for right now. And if I run that, this will kind of show us all the classes or RDF classes that we have in for all the resources in our stage environment. If I go ahead and sort of restrict it, and so what these brackets with the 0, it's saying take the first and just display the top 35. And so if I do that, that's going to restrict it. And here we get a better sense of what the sort of the distribution of classes in our RDF graph. And you'll notice the Sinopia property template. So that is used in constructing in Sinopia resource templates. And so it's probably not a surprise. That's probably one of the most popular things. Let me see, make sure. You can, and then the next most popular one is BibFrame title. You can kind of see through and see that. Now, because it's now in this Pandas Data Frame, and I think there's a comment that also is sort of ahead of us a little bit, but we can actually plot this and create a graph. So I'm going to create a bar graph here, and that just takes the top 35, and you can see we have this sort of long tail distribution of classes. And that's probably not too surprising. I mean, that's a really common distribution if you heard of like power laws, where the majority of your classes or your observations or whatever are on the left-hand side of sort of the bulk of your distribution. And then it slowly peters out and sort of that long tail where you have only 1 or 2 observations. And so really, we have this sort of curve here of that. And I just want to say that Magnus showed how you can actually do this as the top 10 pi, and I'll just go ahead and cheat and use that code that was put in the chat and kind of show you what that looks like. So if I do here, voila, we can kind of see again in a nice pie chart. And again, this is all the sort of built-in functionality that we have with that Pandas Data Frame provides us. So with that, we're almost to our first break. If there are any questions, please feel free to put that in the chat or let Jim know. If you don't feel comfortable doing that, you can email me at jpnelson@stanford.edu, and I'd be more than happy to get back to you as well if you have any questions. And I think with that, we will come back at the bottom of the hour, 8:30 my time, but translate to whatever your time zone is. So in about 5 minutes.
All right, we'll see everyone in 5 minutes then.
All right, I noticed a couple of people are having issues trying to load the stage environment. I would just double check. You can see here I'm on the binder version, clicking on the stage. So you should have some content looks like this. If you, over here on the left here, click on data. If it's an empty, I'm not sure why that happened, but you may try deleting all the files there. You can just sort of select that control, and you can delete those. And then I would go back here to the first notebook and try extracting the data again using this command. That's what I would suggest, but I don't want to spend too much time, but that may be, if you're seeing that JSON decode error that Jesse first posted to the chat, and it may be something there when you're extracting somehow got messed up, but that's what I would guess. All right. With that, I'm going to go ahead and go back here. Just because I'm going to close the previous two notebooks, and now we're actually going to shift to using natural language processing with spaCy and HuggingFace. So, just to quickly let Robin know, so part of what the helpers method in the harvest method in the helpers module, that was my attempt to try to, if we encountered any URIs that was causing that serialization, and just try to parse it out and create a valid URI to be able to use in the workshop. So even though those wording messages are disconcerting, hopefully they'll be fixed if you run it with the create_kg method call. All right, so we'll go ahead and get started here. So first thing, I want to make sure I run the first cell there. So in this particular notebook, we're going to be using spaCy, which is a open source, really popular natural language processing library. And spaCy allows you to do a couple of things. One, you can quickly sort of extract parts of speech from the text descriptions. And it also has a statistical model to extract and identify or tag entities in sort of that named entity recognition, what's sort of referred to as NER. So both of those capabilities are available through spaCy. I'm going to show you where we're going to be using the fast subjects to create in spaCy terminology a phrase matcher, and then we will see how that works, and this will give you an opportunity to sort of show you some of the challenges that can occur when you're working with NELP or other sort of natural language processing or machine learning techniques. So after running this, what we're going to do now, as part of the data that we extracted, is actually a CSV file that Arcadia Falcone at Stanford had put together. That is just a spreadsheet that has two columns, a URL, sort of from the OCLC's fast subject heading, the URL, and sort of the label that was assigned to it. So I'm going to go, and what we're going to do is we're going to read that CSV file into a Pandas data frame here. So I'm going to run this. Let's see. Where am I at? Okay. That's not good. Let me do what everybody is doing locally. So let me delete that. Go back here. Let me, workshop tab is there. Nope, and I deleted everything. Sorry about this, people. run this again. All right. Problem averted. And then, well, let's rerun that. Okay, so we've read in all the fast topics here. Now we can kind of get a sense of what's in this, in the facts data frame. So the shape, when you call it on a Pandas data frame, basically provides you how many columns and how many rows are available. So, and then we're also going to call the info, which gives us a little bit more information. So the shape of our fast topics, we see we have 460,110 rows, and we have 2 columns. And here in the info will actually show us what the columns are and how many values are in each column. And so we have 2 columns, URL and name, and then we have, again, the 460,000 rows there. Now, Pandas Data Frame has a convenience function called sample, which will just sample, provide you a random sample of your data set. And oftentimes I like to run the sample just to get a sense again of what our underlying data is in our data frame. So I'll just run it and I pass in 10 to give us 10 members in our sample. So we run that, you can kind of see here is sort of the index or where it's located in the data frame, the URI, and actually the name or label of what's in there. Now we'll notice here that in the fast names that come back, it does have some punctuation. If I run another sample, maybe we'll get one. Here we go. So you see we have the double dash and we also have parentheses. So when we're going to be creating our phrase matcher, we're going to want to remove those punctuation in it. So that's just something to note of. Again, it's very helpful as you're doing the sort of analysis and then going towards actually applying some of these machine learning techniques to try to understand what your data is and things that may sort of break or cause results that are unexpected results of what you're running. So that's just a sort of a note of what we have in our particular data frame here. So spaCy has this module called a phrase matcher, which is basically allows you to send in to spaCy phrases that are extracted from a data source. In this case, we're going to extract the URIs and sort of our cleaned up names, and we're going to add them as patterns to our spaCy environment or our spaCy phrase matcher. So here, what we're going to do, first thing, we're going to basically import in an empty English vocabulary. And then we're also importing this phrase matcher class. And we're going to instantiate and save in our NLP. So basically a NLP pipeline. And we're going to start with the space English. And then we're going to, from that, create a phrase matcher. And in this case, we're going to say, we're going to send in this attribute lower, which will allow us to do this phrase matching on mixed case. So it's going to basically ignore the case of the incoming data that we're trying to do this phrase matching on. So I'm going to run that. And then just to give you a sense, so I grabbed one of these names, and this is sort of the processing that we're going to do to create a Python list that just extracts all of the text that come out of the name itself. And so here, African-American teenagers education, when we run this strip, so we strip out the punctuation, we replace any double dashes with a space, and then the split just basically uses any white space and create a dictionary, or not dictionary, but a Python list of those terms. So now what we're going to do is we're going to go through those 400,000 plus rows that we have in our CSV, in our fast topics data frame. We're going to extract the URI here. Then we're going to create this name list. And then we are going to run all those names through this NLP make doc. And that all that does is tokenizes it. So it turns it in as well into a mathematical representation besides just text. And then we're going to add that to our topic matcher. So I'm going to run that. And you can see, so it takes a little bit to chunk through all those resources there. Let's see. So it shouldn't take that long, hopefully. So sort of prep us for what's coming next is now we're going to take this phrase matcher and apply it to titles and summaries that are within Sinopia. So we're going to go back and I'm going to run this too. So here, and then, so this might take a little bit of time. Just while we're waiting, you can run multiple of these cells at a time. And so you'll notice here on the left, you've probably seen it already. The asterisk means that cell is running. And if any subsequent cells that you sort of launch afterwards will just be in a waiting state that they'll wait for that to finish. So why is that going along? There, and so it took them about almost 2 minutes, unfortunately. But you can see here, now we have this phrase matcher. And now the next step is we're going to go back to our Sinopia knowledge graph. And just like in the previous notebook, we're going to load our saved knowledge graph for stage. And then we're going to actually start querying that to create a Pandas data frame that we want to sort of use. So here, while this sort of loading, the query that we're going to run here, the Sparkle query, is you see here we're selecting the title, label, summary, and the URL. So, and in our where statement, we're doing sort of optional. So not all of the resources in Sinopia have a title or a label or a summary. And by specifying this optional, it'll just sort of give us that. Now, because this takes a little bit of time, what you can sort of load this staged text nodes into your notebook instead of actually running this. And so let me go ahead and do that so you kind of see. So here, if I do td JSON, so, and then I pass in from our data. Read JSON, sorry. There we go. So now let's just take a look at this, our kind of data frame. So our shape, JSON. So here we have our title, we have the URL, and you'll notice, again, this is sort of sparse where some of our resources have a title, or it looks like hopefully most of them have a title. Some of them have labels, others have summary. So then let's just do an info, kind of get a sense. So again, this sort of breaks it down where looks like all of our resources at least have a title. The label, only about 1,057 have a label in the summary, again, around 1,000. So all of our resources at least have a title. Some of them have a label, and some of them is a summary. So let's sort of see sort of the shape again. It sort of shows us how many columns and how many rows and how many columns. And let's just take a sample of that, and so we can kind of see again sort of this random sample of what's available. Another method of data frames allows you to show the last 5 rows in your particular data frame. So here, this shows us the last 5 rows that we have. All right. Now what we're going to do is we're going to take one of the rows. In this case, we're going to grab row 11,484, and I can show you what that looks like, actually. So this ILOC is a method call that allows you to extract a single row based on sort of this number here, or what's called its index. So if I just paste that in, you can kind of see what that looks like. So it has this title. Our label doesn't have a label, but it does have a summary. So with that, we're going to pass that summary. And in fact, let me do this just so you can kind of see what the summary looks like. So you can see here's our summary text that we have. And we're going to pass that summary into our spaCy NLP pipeline. And it's going to return back this document. And then if you look at the document, it just right now, sort of its default serialization just shows you what the text is. But it also has some additional functionality in it that we'll see later. Here, we can kind of get a sense of the topic matcher that we created earlier. So the process of applying our phrase matcher to any text is once you've created your spaCy doc, you pass it into the doc. Now, I'm going to run this, and all I'm going to do is run this and get a length of how many matches it made. Now, that's quite a bit, over 150,000 matches. And so that's sort of unexpected. So what we can do is actually look at let's look at the first 50 matches and see what is displayed there. Now, we kind of look at what's happening here. This is sort of an internal ID that matches to the URI. And then the second number is its location, basically which word it is, and the start word and the end word. And so these few are matching on the first word. As you can see, it's sort of going through. Now, we can, because this is returning back a list, we can retrieve sort of the first match. And you can kind of see, again, that's that first row here that we see. Now what we're going to do is we're going to refer back to our vocabulary, and we're going to actually see which URI that matches. So if I do that, so what I'm basically doing is from our vocabulary string, pass in the first match, and then here, this is just saying, send in this first value here, this sort of internal ID, and it will return back our fast URL. So if I click that, we can see come and take it. So that's sort of, that's that first match here. Now, we can also, since it's also present in our original fast topics data frame, we can look it up by that URL we have here, extract the first match and display what its actual name is. And again, come and take it canon is what it matched. So if we go back here, so sort of what it grabbed was it found, because we broke it up, it's being very greedy and matching a ton of things. So right now, this phrase matcher is probably not as useful as we want it to be. So there's some things that we can do to the phrase matcher to make it more useful for our own needs. And part of that is if you go back here to this function when we were creating it, we went through and for every single word we made that as a separate sort of token. So instead of doing sort of separating each of those into individual tokens that match, we could change this phrase matcher to just use the entire phrase to match on. So we could go back, and this is where this sort of iterative process is as you're working with your data, as you're applying these techniques, how do you sort of improve it for your needs? So that's probably one thing I would do next is instead of chunking out all of the word phrase, just keep it as a full phrase there. Let me make sure. Okay. Any questions? Okay. So let's go back. Here, kind of see all this. And then let's go ahead and again, I created this get matches helper function that you can pass in a particular a data cell, if you will, in this case, from index 11,484, pass in the title. This method, you pass in the NLP pipeline, our matcher, our fast topics, sort of our source of where we want. And then in this case, the last item to pass into this helper function is how many the matches we want to return. In this case, return back the top 25. So I'm going to run that. And then we can sort of display this. And this makes it a little bit easier to kind of see what the top 25 matches. And of course, that's not as helpful if we don't know what we're looking at. So I'm just going to display this to get a sense. So pocket full of rye. And you can see here, because our phrase matcher was so greedy, it really just matched pocket and most of these, which again is not quite what we want. I mean, we want it to be a little bit more discerning, but because we had created our phrase matcher initially and it parsed out, that's why it's returning back so many results. Yeah, and so that's you can see. We can also run this again here and sort of display. And so again, it would probably be helpful to understand what we're looking at. So advanced examination techniques is sort of the title for this particular node that we grabbed from our data. And as you can see, it's advanced is there quite a bit, and again, really not that relevant to what we're wanting to do. So I just want to have a quick shout out to Jim Hahn, who's our moderator, and he's been doing some great work with the NEEF project and using the MARC collections from the University of Pennsylvania and the new pod service, aggregation service, to do this sort of subject suggestion more at scale. And we have an open ticket in Sinopia to actually add in the work that he's doing, so that as catalogers, as you're entering in a title, for example, it will go and based on all this data he's trained in a NEEF, will come back suggestions that best match that title. So think of sort of opposite extremes, if you will. Where right now, this phrase matcher approach is sort of, if you will, on working on small data, while he, on the other hand, is working really on the big data side of things. So, I just wanted to just make that note. One of the real strengths of spaCy is not just this phrase matcher, but it's named entity recognition, or NER. So in NER tasks, sort of existing entities like people, locations, time periods are identified and tagged for later analysis. we're going to run, and the next part of this, we're going to load up a small English vocabulary. And here, you see I'm running this line here, this cell in our notebook. And that just, again, sort of downloads this core web small model. Now, this is a statistical model that they've trained, that spaCy's trained and made available. They have a number of different languages besides English that you can use. So if your incoming data is in a different language, you can use these other vocabularies, but using the same sort of process that we'll be showing here. So went ahead and downloaded and loaded up this English core web small model. And that's all what this code is, just going out there and downloading it and installing it locally in your local environment. And then now we're going to create a second NELP or natural language processing pipeline that we're going to load this vocabulary that or this model that we just downloaded. So I'm going to go ahead and do that. So now it's loaded. Now we're going to use a different sample from our text, our data frame, and then we're going to apply this in the English pipeline to some of those values that we see. So here, and if I kind of look at the sample, so again, we have this here. Now, so just to give you a sense, when I had run this earlier, I had grabbed a couple of different examples here using, again, this index. And so just to sort of show you, let me print both of these out so you can kind of get a sense of where we're going to be running through the NELP, the NER here. Show that summary. So the first one is Rest in Power. So the title, The Enduring Life of Trayvon Martin. And then the second one comes as a summary, and it's really a novel that Cohen, who's the Secretary of Defense back in the late 1990s in the United States, he wrote this novel, and here's the description or summary of that. So we're going to take both of those, and we're going to run it through our NELP pipeline. And so I'm going to do that right now. So we created these two documents. Now in these documents, all the named entities are tagged and are available through that document object. And so here, entities for the first one, so in this case, Rest in Power, the Enduring Life of Trayvon Martin, we're just going to just display the entity and sort of what it was labeled at. So here, and then we'll do the same for the summary from, I think it's, maybe the title is like Dragonfire for that. So here, so running it on the first one, we have one named entity sort of, and it sort of tagged all this. And again, this is a statistical model. And it tagged that entire title as a work of art. So that's interesting in that it identified actually a creative work within just by the title itself, using this small English model. Now for the summary, we notice there's quite a few more of these entities that have been tagged. So we can see it correctly identified William S. Cohen as a person. Defense, so the Department of Defense, it was interesting within the context of the text, it identified that as an organization. US, it identified it as a geopolitical entity. Dragonfire, now here where it misidentified this as a person, well, this is actually the title of the book. Vietnam, it identified that as a geopolitical, identified more of the people. It also, the sort of baseline NER of spaCy will try to extract like time spans and notifications of that. It identified Democratic, Bill Clinton, a date you can see there, ordinal, and that 20th. And so, so in some ways, it did a pretty good job. And again, this is just using the baseline model, and we haven't trained this model. We haven't sort of optimized it for our particular use cases, but it did go through and do that. The spaCy also has some really nice visualizations that I want to show you. So if you basically, all you need to do is import the spaCy class, and in the first call here, we're going to display it as, we're going to take the summary from the 3087 row in that summary, and we're going to pass it through, and we're going to see what that looks like. So I'm going to run that, and here it basically took those entities, but now put it in more of a context. And this can be really useful if you have short chunks of text and you just want to see the context of how spaCy sort of tag those. And you can kind of see here, it has the people and everything that was up in that long list, but now it's now placed within context of the text chunk that we sent through. The other sort of visualization is, and spaCy is really good with this, is that you can also display sort of parts of speech. So it'll extract the dependencies and sort of the structure, the grammatical structure of a particular text. In this case, in the second cell here, we're going to pass in that title, and we can kind of see what that looks like. So you can see here all the rest in peace or rest in power, the enduring life of Trayvon Martin. It has this nice graphic and sort of shows you the relationships, how what it refers to, the proper noun, verb, and things like this. So this is, again, another use case of what you can use spaCy for in this sort of parts of speech sort of identification. All right, so the next exercise we'll have you work on is go ahead and download and create an Ner pipeline, again using the same model, and then go back to our sample that we have and pick another either title, label, or summary, and just run it through and see if you can replicate what entities were identified with your sample. And we'll maybe have like 4 or 5 minutes, and then we'll come back. And then for those of you who want to do a little bit of extra credit, one thing that I think has been really exciting with Sinopia is that there's been a lot of non-English resources that have been cataloged in Sinopia. And so if you find one in your sample that's a non-English, there's a link there to the available models, and I can kind of show you that. Click on that. That you can use. You'll need to download it like you did the English one, but here we have these trained pipelines are available for you to use. And so if you want to do that as extra credit, go ahead and download a different language model and then run it against your sample. So we'll come back maybe at like 10 after the hour or 9 after the hour. All right. Hopefully everybody was able to at least try this out. I think NER has a lot of promise, and in a couple of the AI projects I've been working with at Stanford, we've been looking at using spaCy to do different types of NER. I didn't have time to go into it, but you can actually create custom entities and train your model on those. So, for example, one of the projects I'm involved with at Stanford is with the Hopkins Marine Station, where we're trying to identify species in context of student reports that go back decades, and extract the species and then sort of co-locate them with locations and create what's called a species occurrence or observation. And that's really helpful in where you're trying to identify how species distributions and occurrences have changed over time. So you can use these techniques and approaches in a lot of different contexts. And I think there, to me anyway, I believe there's an incredible amount of promise in these different types of approaches. So so the next section, what we're going to do is we're going to look at and again, this is me sort of going off a little bit of a tangent about how can we use, if we have available full text for a catalog resource, how can we sort of combine the two and really improve workflows for catalogers or other library staff using something like NER. And I just want to have a great special thanks to Tim Thompson at Yale and Greta DeGroat at Stanford for providing some examples of catalog Sinopia resources and their corresponding full text. So the first thing we're going to look at is this title called Alarmingly Suspicious. And here's where it's the actual record in Sinopia production environment. And we're just going to download and load that up into a Sinopia graph. So I'm going to go ahead and run that. And so if we want, again, just to see what it sort of looks like. So this example one graph, if I want to serialize it. Now, the reason I'm putting decode is because the default serialization returns back your graph in a binary format, and it doesn't print nicely. So this decode converts that binary format into Unicode so we can display it. So I'm going to go ahead and run that so we can see what our graph looks like. So again, this has been cataloged using BibFrame, and sort of a resource now that we have available. Now, the full text was then extracted from HathiTrust, and there's a link there to go to HathiTrust. And I included it as part of your data. So this resource and the full text should be available in your data subdirectory there. So what we're going to do is this line here, we're going to open that file up. We're going to read it in, and we're going to save all the text in this variable called example1_text. And then this second statement here, we're just going to see how many characters are in this particular full text. So I'm going to run that. And so we see here there's 61,249 characters that are in this text here. So now what we're going to do is we're going to run our English NLP pipeline on this text, and then save the resulting spaCy doc in this example1_doc, and then just to see how many entities were identified. In spaCy, the docs are available in this ints property of the document. And so this is just displaying how many there are available. So I'm going to run that. And you can see here that it identified in that all that full text 576 entities. So just as sort of get a sense, we're going to iterate through all those entities, and we're going to save into two different Python lists: the people, so all the people that are identified, and the locations. And so that's all this is doing, this for loop here, is we're going through all the entities. If the label starts with person, we're going to add it to the people dictionary. If it starts with the GPE or geopolitical entity, we're going to save it to our locations. And then this final line, we're just going to output how many of each of those lists we found. So for people and for locations. So I'm going to run that. And we found 327 people with 20 locations. So if we look at the people's list, we'll notice, and let me do that, in fact. So all I have to do is just type in people, and you can see here, there's in fact a lot of duplication, and this is actually a play, so it's not nonfiction. It's a play, and it has dialogue in it. So I'm just going to collapse that. So what we're going to do is maybe try to figure out a way to remove the duplication. And in this particular approach, we're going to go through all the people, and for each of the entities, we're going to take the entity, we're going to take the actual text of it, we're going to split it. So by splitting it, we're going to remove any of the characters, like new line characters or anything like that. It returns back a listing of the words itself. And then this set will basically, this is a Python reserved word that creates a collection of items that are all unique. So it'll remove all the duplications, and we'll do those for both people and locations. And so now we'll see how much that reduced it down. So we dropped from 327 to 114, which is a little bit more manageable. And in our locations list, we dropped from 21 to 12. So that, again, just by sort of removing the duplications, we're able to get our lists down into a little bit more manageable size. Now, I thought, well, now that we have these names, what can we do with it? So one idea I had was, what if we use the OCLC VOF search on our people and see if we can search on those terms and see what returns back. And so I'm going to go ahead and do that and run this. So it's going to iterate through and find those. Now, just in interest of time, and I realize that this session, we only have a few more minutes. I have this example too, which does something very similar with the full text there. I think I'm going to skip that example because I definitely want to get to the fourth notebook, which is using HuggingFace to do a similar thing. So while that's sort of running, I'm going to open up the HuggingFace notebook, and then we'll sort of talk about what HuggingFace is, and it's another Python project that uses a very different architecture to do a lot of the same things that spaCy does. So this is cranking through. So we have 114. So that's almost done, and then maybe I'll come back to this and just show you what the sort of output of that while we're sort of waiting. So, well, spaCy, I think, provides really good enough NER capabilities, and I didn't really touch upon how you can train some existing models like the spaCy English model to improve the NER recognition. There's really been in the past probably 3 or 4 years really an explosion of accelerated very good NLP models, and HuggingFace, which is a company that's sort of specializing in the state-of-the-art models, provides a really easy to use NLP pipelines to do various things within sort of a natural language processing. And we're just going to quickly sort of look at that. So first thing I'm going to do is run this. So the really big difference is that I imported this pipeline here. Let me again load in our text nodes. So this stage tech node, so when, just for your information, when I ran this sample or this data frame, I saved it, and it's also persisted in your data subdirectory. So I just loaded this up, and I'm going to take 10 a size 10 sample, and as you can see, in this case, all we have are titles and no labels or summary. So I'm going to run the sample again, keep on running. Hopefully we'll get summary. Okay, so here's an example where we have either this looks like Japanese, Chinese, and then we also have French. So again, I sort of mentioned before, there's one thing really exciting with Sinopia is all these different languages and material that people have cataloged using spaCy. So let me go back down here. I think this probably should have finished by now. And it did. So we can kind of see what the results. So here, just basically we saved the VIAF URI and then the sort of label that's associated with that VIAF authority there. So you could see perhaps a workflow where you could take these and add it back if you wanted to into your original graph to sort of improve the cataloging record that's stored in Sinopia. All right, now back to HuggingFace. It has a NER pipeline. And so I'm going to grab an example and just show you. So this is a Star Wars example. And so this is sort of a description of this particular novel. Now, since we imported the HuggingFace pipeline, we're going to create an NER pipeline. And so I'll run that. For those of you who are running on Mybinder, when you run the first time you run this, it's going to go out and actually download a model. Since I already have it loaded locally, it's a little bit faster. But when you run this in Mybinder, you'll see where it sort of goes out and some messages as it's downloaded. Now we're going to basically do the same thing, pass in this summary into this NER pipeline. So I'll run that. And then we're going to go through and sort of print the results of that. Now, these look very different than what we saw in spaCy. And so one of the differences is this is a little bit lower level, and it's doing NER in a different way. One of the things that's nice, it does provide us with sort of a score, sort of a statistical score of how confident the model feels that this particular entity has been identified. It gives you the index, the character index, where it starts and where it ends, and then what it sort of matched. Now, in this particular case, it also, I should mention that this particular HuggingFace model that's being used underneath does do text masking. So that's a technique to help improve the recognition. And you'll notice as we look through here too, it doesn't have as many different entity types as spaCy does. So we have these I-LOC, I-PR, and I-org. So those basically are for a person name, organization name, location, and I-miscellaneous for a miscellaneous entity that it identified. Here, again, just as I mentioned before, it gives you a statistical score, and it also does this character masking, which is you can see in the above results are these pound signs or double pound signs. Another really cool feature that HuggingFaces provides is using a different model. It can give you sort of summarization of text. So what we can do, so you pass in a long string of text, and it will do its best based on the millions of words that model was trained on to provide a concise summary of the text that you pass in. So I'm going to run that. And again, I'm going to go ahead, and while that's running, we're going to open up and use the unreliably suspicious full text. And then we're going to pass it in to this resource here. So I'm going to do that. And lo and behold, we got an error message. So if we go down and we sort of look, we get this index out of range. Now, HuggingFace and these models have a maximum length of text it can do a summarization on. So the fact that we're sending in 60,000 plus characters, we sort of overloaded the model and it didn't actually perform this summarization. Now, there's a way we can get around that, and how we do that is to basically chunk our text out into much smaller sizes, and then we can pass it into the summarization, and we can summarize that, and then sort of combine the summarizations at the end as sort of an approach. Now, I think I'm going to avoid doing that at this particular point because this does take a little bit of time, and we're at time for this session. But if you, I basically saved to the data directory a listing of all these summaries. So if we can actually load those up, and during our break, I'll go ahead and load that up, and then when we come back, I can show that to you. So now I think we're going to take a 10-minute break, and then when we come back, we're going to look at using Fast AI and PyTorch to do actually some training and classification. So, and also look at the chat to see. Let's see. Yeah, so we will, this is all being recorded, so you can go back and review any of this material. And again, then there's links to all these notebooks and its own GitHub repository as well. All right, well, thank you, everyone, and I'll see you in 10 minutes. All right. Hope everybody had a good little break there. So just to kind of see what these summaries look like, let me just display this. So part of what we did before was basically chunk out every 500 words and send it through the HuggingFace summarization, and then just add it to this summaries list. And here is, you can see there's quite a bit of text there for each of those chunks. So the what we could do is sort of look at how then can we get that large summary down to a smaller summary. And with what the rest of the notebook does is then takes those, and this is just an experiment I did, was take this long list of summaries and ran those summaries again through the summarizer and tried to get down to a much more manageable size. And then the sort of this last idea was, now that we have this summarization text, and so here is the end result is I saved at this as a literal here in this particular instance, and then just adds using the RDF-lib library, adds that triple to our existing Sinopia resource. Now, if I'll be co-presenting in this afternoon on another Sinopia related tutorial, and there I'll show you actually how to use the Sinopia API if we wanted to add these triples and update the actual resource up in Sinopia. I'll go through a process on how to use the Sinopia API to do that instead of using the editor. So anyway, there's also, for those of you who want to, there's another exercise about basically picking a sample and then running it through both spaCy and HuggingFace and just compare the two to see what the similarities and differences are in a particular sample if you pass it through the Ner pipelines for both. All right, so our last notebook that we'll be going through is looking at FastAI, which is a nice library that sort of sits on top of PyTorch. And PyTorch is a really popular machine learning environment that you can use to train neural nets and other models. And it's widely used in academia for research, for machine learning research. And it's becoming more popular in industry as well. And I should also mention PyTorch is one of the big sort of behemoths out there for machine learning. The other one you may have heard is called TensorFlow. PyTorch is actually open sourced by Facebook, while TensorFlow has been open source and is supported and managed by Google. So both of those very large technology companies are what's behind these really popular machine learning libraries. So the first thing we do, of course, is initialize and run, and so load in our libraries and dependencies. Sort of the new one for this notebook is that we're loading in all the FastAI tabular libraries and modules. FastAI also has libraries. So this is for tabular data. So think of it more like spreadsheet, if you will. They also have libraries for doing machine learning on video, audio, and images as well. But we're just going to be, and I should say too, text. They also have NLP libraries through FastAI as well for doing very similar NLP that we saw and worked with spaCy and HuggingFace. First thing we're going to do is load in the RDF, the text data frame here. Now, what we're going to do is, and so this, I know some of you attended last year when I gave a presentation at the LD4 conference on how to use machine learning to classify incoming or unknown RDF by existing resource templates that are in Sinopia. So what we're going to show you now is sort of building on that, doing the next iteration of that work. And we're just going to go through sort of the process on sort of extracting our data, training our model, and seeing the results of that, of doing that training. So the first thing we're going to do is we're going to run a Sparkle query against our RDF knowledge graph for stage. And we're going to extract the templates and the URL for that. And we're just adding an additional filter to make sure that it's an URL instead of like a blank note. Another thing, just to sort of filter it out, in this case, since we're using resource templates to sort of test what as part of our testing, that we don't want to include resource templates in our training and validation data. So all this line here does is make sure that we don't do that. So now, if you sort of look at our data, we're going to pass it in to and create a stage data frame using Pandas. And this line right here, so if there's any missing values, we're just going to fill those in with a 0 instead of having a not or a null value there. And so now next we're going to actually sort of see the shape and the info. So we have 239 columns, and we have 1,000 or 10,712 rows in our frame. And why? I think something's okay. So what this is doing here is we are we have our row, we have our URI, and then sort of the approach we're taking is we're creating a frequency of predicates in our data. So for one resource, if a predicate exists, it gets a 1 or it increments. So it's sort of weighted. So if I have like 5 titles, I'll have 5 here as a numeral value. We also have the template, and then you can see for the most part, and then all the possible predicates are available. And for those that the resource doesn't have, we just assign it a 0. And that's what this 0 does there. So that's our base data frame. And now we're going to take the next step, and we're going to split it into training and validation. So in a mini machine learning context, what you want to do with your data set is you want to split it up into 2 sort of buckets. One bucket that we actually train the model on, and then the second bucket is a validation. So it basically validates that the results are correct as we're training the model. In most of the time, we can just do it randomly. So I have a data set. I can say, give me 20% of that data set, and I'm going to just randomly pick the data, and we'll use that to validate our training, as we're training the model. One of the key requirements, though, is in this case we're going to be using what template was being used in the record as sort of our dependent variable. So as that dependent variable, so what that means is that given this frequency of predicates, we need to make sure that our training data and our validation bucket or data has all the labels in both. So if, for example, if I have a template that's in my training data set, that's not in my validation set, that's going to cause an error as we're training because it needs to be in both. So, that's that's not uncommon depending on what task you're trying to do, and that you need to do some manipulation to create your training and validation set. So I had to create this method to be able to do that, and I really want to quickly just show you the sort of the approach that I took here. So going here. So here is this function called create splits. So we pass in the data frame. In this case, are all of our stage data, and then the second parameter is the valid percentage. So what is the cutoff of our that we want to add to our training versus our validation? So in this case, we send in a default value of 0.2 or 20%. So first thing we do is we create, now this L is actually a special extension of Python list that's provided by FastAI. And then we go through and we group all of our data by templates. So each template comes with, we group everything there. Now, one of the things I had to do before we even go, we have a number of cases. There's like 100 or so resources in our original data set that didn't have, there's only like one example of a template. Because we can't really split that up into training and if there's only one example of it in our data set, we can't use it because we can't split it between the two. So one of the things I did was filter those out so that we don't have that there. So then so we go through, we clump basically or group all of our templates. Then we take all those templates, shuffle them, so they're all random in this group for a particular template. Then this line here is where we ensure that at least one of those resources that has that template is our training and one is in our validation. And then for the remaining values, we go through and randomize whether 20% of those will go into our validation, while the remaining 80% go into our training, and then we just return that. So there's that. So now, so that's what's happening there in our data set. So that's what this sort of pre-processing does. So a couple of things here. So that's what this cell is doing. The first thing we're doing is ensuring that we don't have our URI. So we're moving the URI because that's more of an ID, and we're not really going to be needing to train on that. And we're also removing the has resource templates, or our dependent variable. We want to remove it from our training. Then this line, this cleaning line, is basically returning back everything that has a duplicate and removing the ones that are just the singleton. So that is what that's sort of the data set that we pass in then to the create splits method. So now if I run this, we can take a look. And part of what these splits, this here, you'll notice there's two pieces or two lists that are returned. The first one is our training data, and there's 8,338 records or resources in that. Now the list itself is just referring to, if we kind of look back here, to the index. So we're not, so in the training, it's going to look up in the data frame to determine the FastAI libraries that we're going to be using through the learner to determine whether it's in the training or in the validation set. And so the first one is all of our training data, and there's, again, 8,338. And then our validation set has 2,265. So this, in terms of machine learning, this may seem like a lot, but actually it's a very small data set. Sort of what's happened in as sort of explosion of AI and all the gains we've had in recent years, a lot of those gains have occurred because you're dealing with millions or even billions of observations, especially if you're a large technology company, let's say like Facebook or Google, who's trying to do analysis using all their huge amount of data they have. So the fact that we have, just over 10,000 observations is really, in the scheme of things, not that big of a data set. Then what we're going to do is we need to extract all the predicates as sort of columns to pass in to the FastAI tabular pandas, which takes our pandas and converts it into a format that we can then use to do further training. So, so that's all what this line does, is it goes through and creates that, let's see, since I already used, we want to keep the value there as a predicate. And so if we show this, we can see, you know what, let's do this. So somebody that was off by 1. I want to pop the template out because we don't want that in our actual independent variable. So we pop that out. Now we should see there's all the basically predicates that we have available. Now we're going to go to the next step, and using the FastAI, we're going to pass in our clean data frame. The procedure, so this categorify, what that will do is apply, in this case, to our dependent variable, our templates. It basically takes that full list of predicates that are all URIs and converts it into an array of numbers that we can then use as sort of our dependent variable in our training. And so it creates a category. So every predicate has a location in that array that we can then go back and look up. You'll notice here the Y names that tells the tabular pandas that's our dependent variable. Also that it's a category, and then the splits that we created here, we also pass that in as well to this. So now we can take a look, and here we can just grab sort of what that underlying data looks like. And so that refers back, and so we can see sort of the last two, and that's sort of very similar to our incoming data that we had. Now, our final step in this part of the workflow is actually create a data loader that we can then pass into our model, our learning model. And you'll notice that there's this method that the tabular pandas provide, data loaders. And you see this parameter BS equals 64. That's just the batch size. It's short for batch size. So a part of the training, and we kind of saw this before when we're using the HuggingFace, is that a lot of these models need to be sort of batched up to be processed. And another reason that they use batches is that, particularly for using GPUs, or graphical processing units, with these very large data sets, you ideally want to run them in parallel. You don't want to run everything sequentially. So by specifying a batch size, if my laptop had a GPU that we could use, it would batch those up into 64 chunks and spread them across your GPU to train everything in parallel instead of linear or sequentially. And we can actually, the loader itself provides a way to kind of show you an example of a batch. And so that's, I need to run that first. So now we can run show batch, and you can see here's, again, should look very similar. And that's an example of a batch, a partial batch there. So the next step is we're going to take our data loader. One of the metrics that we're using is basically just an accuracy. And if we had time, we could go into more detail on what that actually means. But we're now going to create a learner, which includes our model. And we're passing in our data loader, and we're passing in what metrics we want to evaluate that model with. In this case, it's accuracy. So I'm going to run that. So if you kind of see here, we can sort of see some things that go along with our model. So I'm going to actually display this. And this will kind of show, and this is where it ties now to PyTorch. So our stage learner has a pretty simple 3-layer model. And here it's in this sort of sequential order. So the import or the input layer is this first layer, and it sort of linearizes it, and then the ReLU will sort of normalize it, and then it'll batch and train it. So the first one. And then the output of this is passed to our hidden layer, which is this middle layer, which does a very similar processing. And then finally, our output layer just runs it through this training layer and outputs it. And so, so you can see here, this sort of breaks down that first input layer with a linear, and there's links there to the PyTorch documentation for these. We can actually run and pass in. So FastAI has this idea of a learning rate that helps us sort of determine the optimal learning, or how we can train our model. Now, if I run this, we can sort of see, so tabular model, we did get a warning message, and you can see sort of where the graphically what our learning rate is. Now, ideally, we want our learning rate right around here before the graph comes up. We're not actually going to use the learning rate for this example, but you can play around with the learning rate to sort of optimize your training. And we're not going to do that, but this is how you sort of iteratively sort of improve the accuracy of your model. So what we're going to do now is we're going to run our model for 5 epochs and try to fit our model. So I'm going to run that here. So you'll notice as it's going through, our accuracy is improving. And part of that, how this is using our remember our validation set and that's different from our training set. So part of the accuracy metric is comparing what we predict in our model versus what the validation says that model should have. And that sort of helps us gauge our accuracy. Now, with this model, what's really interesting is it went from 63% accurate to 74, almost 75. So that's sort of encouraging to see that based on our incoming data, our model can predict sort of an unknown resource. What is estimated that it can, it's about 75% accurate. There are ways, so there are multiple ways if we want to improve our accuracy. So one method is actually to pass in a learning rate, so we can sort of shift this and see if that improves it. Another way is improve our data or add more data. Typically, the more data you have, both in your training and in your validation set, the better your model is going to be. So it'd be really interesting to see if we, used, I don't know, the Library of Congress has millions of BibFrame records and RDF or ShareVD or some of these large sources of linked data. We could probably, with a much larger data set, improve our accuracy as well. But for just the 10,000 observations that we have, this is pretty good. So now, if we want to sort of show the results, you can kind of see if we come over here. So this basically takes an example and it gives you a prediction of what template it thinks it is and how confident it is, or its prediction. And you can see for this sample here, some of these are higher than others. So in this case, it's for this particular resource, RDF resource, it's 92% predictive value that this is the right template. Others are not so good. I don't know what the 174, so I'll have to research and see why we're getting that prediction. But we can sort of test this. And then I'm going to pass this in, and we can kind of see. So now if I display the row, so this grab a model. So this template. Now this is, if you want to see this. I'll show you something. Let's see. It's not. Nope. I don't want to do that. Let's do something. Let's see what's contained. I was using off an older version. This is I'm going to have to go back. I'll update this later, as I don't want to spend too much time here, but we can go back from the template and look up to see what is predicted resource template that the model has sort of predicted. Now, so I have as an exercise having you try to do this, but with using our production environment instead of our stage environment that we have here. So why don't we take maybe 5-6 minutes and have you work on that. And then when we come back, what I'll do is I'll actually open up the notebook that I have the answers, and we can go through and see what the answer was for that. So we'll come back in about 7-8 after the hour. All right. So I opened up the 06 notebook, and I scrolled down to the bottom. And so in our data, we do have the production JSON available. So we can basically do the same thing that we did before. So we'll run this to create our predictive. We'll run this. Now, just because we had an issue, make sure this, no, it's not what we want. And then create a title of pandas, create a data loader, create our Luna, and then if we run this, you can see that our accuracy on production is very similar to what we saw on stage. So one thing, if we want to just take a look at our splits, there it's much smaller. So there's not as much data in our production environment. So, 2635 in our training and 805 in our validation data set. All right, so I think that's all I have. I hope everybody has learned some things. I've learned some things doing this live, and like I said, I'll go back and update the Fast AI notebook there, and then if you have any questions, please feel free to again email me. I'll drop in my email into the chat, and I hope that it, oops, sorry. There we go. So, but please, I'm really interested in this topic and seeing how our profession as a whole can start really taking advantage of really this. A lot of these great tools now are becoming much more accessible. I mean, you don't have to have a PhD in computer science to be able to start using these machine learning tools and techniques. And I would also mention too that in the first two notebooks on the visualization and creating, the knowledge graph has a lot more that's also available that we didn't touch on. And you can do things like doing shackle validation. You can do inference using the knowledge graph. So there's even in that piece, if you just use the first two notebooks, you can get really further along in understanding linked data as a network graph. So yeah, so I'll open for any questions that people may have. And again, thank you everyone who's on the West Coast. This is very, very early, but now it's starting to get a little bit lighter. Yeah, thank you everyone.
Right. Thanks, Jeremy, for all of this. I think it'll give us many of us, a lot to explore. The recording of this and many other recordings from the conference will be available on the LD4 YouTube channel. Also, if you would like to save the chat, we'll try to find a way to post it, but you can do this locally by clicking on the three little dots in the lower right of your chat box and click on Save Chat. Otherwise, we'll stick around for a little bit if anyone has any questions. And after that, we'll close this up and there's more to explore. All right, Jeremy, I think it looks like people are starting to drop off. Should we call it?
Sure, sounds good. Thanks, Joe and Jim. I really appreciate all your help on this.
All right. Thanks a lot, everyone. Have a good rest of your